Justin Miller, Card Physics here, and we are going to continue onward with some capacitors. All right, so let's just go ahead and do that, and we're going to take a look at a parallel plate capacitor and just talk about charging it. We're not really looking at the time evolutionary behavior yet. We will, but let's look at charging a capacitor. With a source of potential difference. Which is ultimately a battery or power supply. Source of potential difference? Oh, great. So we're going to take ourselves a parallel plate capacitor. It's the easiest thing to look at. I can take some plate here. I can take another plate right here. And we can have that those two plates are right now electronically neutral. Just as many as protons as electrons on both plates. So we've got a neutral system. There's no electric field in between them. No charge separation. That's great. So I'm going to go ahead and connect these plates here. I'm going to put in like a little switch, actually. So this is a switch. And I'm going to connect these to a battery. So this battery can have a positive terminal and a negative terminal. We'll extend it out a little bit so I can write battery on it. Battery, we'll say that that's the plus terminal, that's the minus terminal of the battery. And we note that the battery is generally denoted to have some sort of voltage. The voltage of the battery, 1.5 volts, 6 volts, 12 volts, 24 volts, some number of volts. And that voltage is the potential difference across the terminals of the battery. The voltage of a battery is the potential difference across its terminals. So we've got this source of potential difference, the battery, we've got some voltage that it has, great. And what else do we have? Well, this little switch right now it's open, which means that there is no conductive pathway for the charges here. But what I want to be able to do is close that switch and see what's going to happen. So again, before closing the switch, it's neutral. Closing the switch. There is no net charge separation. After closing, there will be. How was that? So we go ahead and close this switch. Complete the conductive pathway, and what happens now is that the electrons on this plate are going to sweep over to this side. You say, well, why? That's what the source of potential difference does. This battery sets up an electric field in these conductive pathways that are connected to these conductive plates. And what happens in conductive materials? Electrons can move around, right? So if there's an electric field that's housed within this conductive pathway that wants to move electrons around, some of the electrons are going to move, the conduction electrons, and, well, the electric field's set up such that it follows the pathway and ultimately does this. So the battery isn't a source of electrons itself, It is the conductive material that is the source of the electrons. So what we're going to have is, electrons are going to come off this plate. And the electrons move onto this plate. That's what the battery makes happen. Moves the charges. So now what happens here? Well, the electrons that came off here leave a deficit of electrons. So this one's now positively charged. Those electrons that came off are swept on over here. And there we have an abundance of electrons in equal amounts. So now we've got a positively charged sheet and a negatively charged sheet. The charge separation is Q because, well, that's how much charge came off one and one on the other. And what do we get? Well, in between these sheets now, there's an electric field. Once all of the charges have moved over, all that will move over, we've got that there's some potential difference across the sheets, and yeah, there's some distance that these sheets are separated by. There's some surface area of the sheets and such, but mostly we are concerned with the potential difference and charge. Plus Q total and minus Q total. So this is what we've got going on here. Well, this doesn't happen instantaneously. It takes time for the electrons to come, move over here, and then you may say, well, when do they stop moving over there, right? When is the capacitor fully charged? That really depends on the potential difference of the battery. It becomes fully charged when the potential difference across these plates is equivalent or equal to the potential difference across the terminals of the battery. I'll explain why that is momentarily. Capacitor is fully charged once the potential difference across its plates is equal to that of the potential difference across the terminals of the battery. Terminals of the battery. All right. Why is that? This is because the conductive sheets act as extensions of the terminals. Of the battery. Ultimately, having this conductive pathway connected to the sheet here means that this sheet is connected fully to this, basically acts like the terminal. This sheet here, when connected to this, acts like this terminal. And thus the potential difference across these sheets has to be equivalent to the potential difference across the terminals because they're just extensions of it. Whatever potential this is at is the same as this. Whatever potential this is at is the same as that. So the potential difference across the sheets is the same as the voltage of the battery itself once it's fully charged. Now again, it takes time for the electrons to move and produce that overall effect, but that's the terminal case in a sense. Fully charged, potential difference across the plates is equal to that of the source. All right, so what do we get out of this? Well, let us name the potential difference of the source of the battery. We're going to call it something else. We call potential difference of the voltage this is a scripted E, and it stands for EMF. It is some number of volts, but we utilize this so we don't start getting it confused with the potential difference across the capacitor. So typically we don't use delta V for batteries, we use this E. And E equals what is called EMF. EMF stands for electromotive force. It's not a force at all, so it's kind of a misnomer, but this is what it stands for, and it signifies the working potential of the battery. Batteries have internal resistance. We haven't gotten into anything like that, so we're just going to assume this is kind of an idealized case where the EMF, or this script E here, the potential difference of the source is equivalent to the voltage of the source. So if this is a 1.5 volt battery, hey, this is equal to 1.5 volts. 6 volt battery, this is equal to 6 volts. So kind of just get used to this little scripted E, and we use it for source potentials. Batteries and power supplies, we use this. That's a little note that. All right, so when it's fully charged, the plates act like extensions of the battery. Thus, delta V is equal to that script E when fully charged. So what does this give us? Well, if we go back to the definition of capacitance, C is defined as Q divided by delta V. Well, for our particular case, when it's fully charged, C is equal to Q divided by the source potential voltage. Now that is Q total, that's the amount of charge. We increase the source potential to something else, well, then we'll sweep over some more charge until the potential difference is substantiated by that particular charge separation. So that's how it's all kind of connected, is the more charge we sweep over, the greater the potential difference is. But we need something to actually produce the potential difference, and that's what this battery is for, the source of potential difference. So that's it. That's what we've got going on here. So if we wanted to know, say, how much charge is separated, we'd have to know the capacitance, and we'd have to know the source potential voltage as well. Well, once we know those two things, we can figure out how much charge is separated. Pretty cool. All right, so that's kind of how this works, or the end result of connecting a capacitor to a battery. Fully charged, there we go. Yeah, I think we just leave that at that. And yeah, we'll keep this one a little short. We'll be back to do some more of this. All right, continuing on with the capacitor, what we also want to look at is the energy store, to get the idea of how it stores energy. You say, oh yeah, it stores energy, how? Energy stored by a capacitor. All right, so imagine this. You take two sheets that are conductive but completely electronically neutral. start with 2 neutral sheets. What we want to think about is taking electrons off of one sheet and putting them over onto the other. So this one's full of electrons and protons, this one's full of electrons and protons, and what we're going to do is start taking off electrons. Start to remove electrons from one sheet. Place them on the other. So we get some little tweezers, some electron tweezers, if you will, and we say, oh, there's an electron right there. Now again, this is neutral right now. What we're going to do is we're going to take that electron and we are going to move it over to this sheet. Then we're going to put it right here. So take an electron, deposit over onto the other side. Does that take energy to do that? And the answer is yes, it does. Why? Because the second we remove this electron from the sheet, now the sheet has a net positive charge. Because as one less electron than proton, right? This electron's attracted back to its parent proton that we just took it from, or attracted to the sheet because now there's an excess of positive charge. So for us to pull it over here takes some work done against the electric field, right? The electric field is doing a negative work in a sense, and just say moving charge, in moving the charge, negative work is done by the electric field produced by charge separation. Takes place due to us removing it, right? All right, so we took one electron over. That takes so much work done. The electric field does some negative work. And yeah, you start thinking about the work done by a point charge and moving, the work done by the electric field and moving a point charge through the electric field due to another point charge. So we've got a proton here. We've moved this electron through the electric field due to the proton. So potential difference that we moved it through, there is a change in potential energy. Potential energy is increased. But we stick it over there, right? But now we take another one. First, then we take another electron. And what happens? Now we take this one and we want to move it over here too. We want to move it over, but this one's harder to move over than the first one. Why? Because now once we remove it, there is a net charge of 2 protons that are attracting this one electron over, and it feels the repulsive force of this net charge of 1 electron on the other side. This one's harder to move over to this side because we've got 2 protons attracting it and 1 electron repelling it. So we store more energy in moving the second one over than we did in moving the first one. Then what? Well, then we move another one. That one's even harder. Move another one. That one's even harder. Move the next one, the next one, the next one. We start moving millions over. Billions maybe. A whole bunch of electrons. And every one successively is harder to move than the last one, and more energy is stored. And the electric field gets stronger and stronger, and the potential difference that we're moving the electron through gets greater and greater. So that's the idea with the energy stored. It's equivalent to the overall work done against the electric field, or the opposite of the work done by the electric field is the energy stored. All right, so that's the idea with this. How are we going to actually get that? Well, that requires that we treat the system, or generalize the system to be that we're moving a large number of protons over, large number of electrons over, and that we can treat them as somewhat continuous because there's so many of them. Otherwise, we have some giant sum with a billion, a trillion terms. I don't want to sum up something with a trillion terms. That just doesn't seem too efficient to me, right? Probably not to you either. So, if we treat the electrons being moved as continuous, which of course they are not continuous because they're discrete, but if there's so many of them and they're so closely packed together and all that good stuff, it's a good approximation. So we'll say for an approximation, it can be shown that the energy stored by a capacitor is, we use U sub C, energy stored U, and then sub C for capacitor is equal to 1/2 times the capacitance times the potential difference across the capacitor squared. Kind of looks like the formula for a kinetic energy. Kind of. And some people have made correlations with, hey, that's like the counterpart to mass, it's like the counterpart to velocity. We're not talking about mass and velocity there. Capacitance, potential difference across the capacitor. So let me just write this out. U sub C equals energy stored. C equals the capacitance. And delta V sub C is the potential difference across the capacitor. Say potential difference across the plates of the capacitor. There we go. So that's pretty much that for just stating it out. Now, you can of course show this as well. So that's more for the calculus-based course because we got to be utilizing continuous charge distributions. So at that, all right.